Hi, so I wanted to go into a little bit more about the design and construction of this based on the comments that people have been making. And I'm going to give a bit more detail on this stuff because I kind of just assumed something, and of course that's always a mistake. The first thing is the construction of it. Now, we've got it laid out here in a linear fashion, and there's a reason for that. The main reason is it's clear to see the blocks involved in a unit. It's clear to see what bits you need. Obviously, you need something to drive it. You need something to move the air. You need something to direct the air. And then you need something to cool the air. Note I say something, because there's so many decisions you can make about this that are suitable to you. I've made it like this because we can follow the blocks. It's really easy to see what those blocks are. But let's deal with this bit first. This bit is a bellows. It's a bellows of 100 millimeters in diameter. And I'll give you a close-up of it and we'll talk a little bit more about how it's constructed. So here's the inside of the bellows box. The bellows itself, remember we did do making a bellows, so the bellows can be any shape you want. This is just bought off the shelf, this stuff. I just put a bit of plastic in one end, went round it with tape to seal it, drilled a hole in the other end, and hey presto, that's what we've got. Then that's glued to this board here, which carries this steel rod there on bearings, and they're in this guide so that we get a nice slide motion. Here is a guide rod that goes through a linear bearing at the centre, and then we can either use that to drive it, but we'll have a look at other options in a minute. Now, this bellows is only this size because that's what I bought. If I want to shift a volume of air, I can either have a bellows that's that round and moves that long, or I can have it that's that round and moves that far. It just depends, really. That will shift the same volume of air. So if you don't want as much travel, but you want the same volume of air, then your bellows is going to have to be bigger in circumference, but not travel as far. So you can change the shape of that bellows depending on what you want. This long linear design illustrates to you how to do it. If you want a more compact unit, then just make a more compact but larger surface area bellows, and hey presto, you'll have a more compact unit. Now the bellows gets driven, in my example, from this rod here. That rod is just a guide rod, really. There is also another rod sticking out right there. We could drive it from there as well as we could drive it from here. It doesn't really matter, both will achieve the same effect. So if I drive it from there, that guide rod helps keep it true as I drive it. Or if I drive it from here, then this rod helps keep it true. So it doesn't matter where I drive that from, I have lots of choices. It doesn't matter whether it's long and thin or short and fat, completely up to you what it is you do. The function of this is to shift a certain volume of air efficiently. That's what it does. Now you don't even need to have a bellows, but you do need to perform that function. You must move that air. How you move that air really is up to you. It's one logical block of an AC unit. Got to move the air. We chose to move the air using bellows because actually they're very efficient. But you could use a fan if you wanted to. There's absolutely nothing stopping you. But you do need that logical unit of moving the air, and that's what this bellows does. Now the bellows will just move the air in a single direction, out here. We need to control that airflow, and for that airflow control, we made this thing. This is a valve chest. I haven't put the top on so you can see inside it. And there is the two valves that we made in the previous video, arranged in the direction that I want them to go. It doesn't matter which direction you want. Now I made these as big circles because I think they look pretty. But of course it gives me a box of even size, but it doesn't have to be. I could make that box half that size and just put the valves on as linear valves. I would, instead of cutting a circle, I'd just cut a straight block, exactly the same way. Now I used this rubber. I use this rubber because of what I've got. You could use a bit of leather, a bit of plastic, anything that performs that function of flapping in and out. So there's just so many choices. The geometry is only chosen to illustrate the logical block of what's actually required. The requirement of this is once you're moving the air, you need to move it in a direction. And if you want to move it in a direction, you need some kind of box that will direct it. if you want to actually have it from collecting from one side or another side, you're going to have valve control. But you don't need to have valve control. You can just push the air in and out of the same side. It doesn't really matter. I want to be able to take the air from a cold space, like a cellar or a crawl space or a shaded area, something where it's already cooler, and draw it through here and make it even colder. That way I think I'm using the inherent capability of my environment around me to create cool air, and therefore reducing the energy cost, because that energy of creating cool air has already been done for me. Equally with the hot air, if I redirect from the loft out here, where the loft is going to have hotter air, it's not going to be hot enough in the deep of midwinter for sure, but it is going to be hotter than where you're sitting. So part of that energy that was used to heat that air that would normally be lost is being recaptured by using a valve chest. So the valve chest not only directs the flow of the air, because you can direct the flow of the air, you can gather it from already existing resources like the cellar or the loft. Reuse it so you don't have to do as much heating again, and therefore create a more efficient system. So that's the job of the valve chest. It's another logical block. It doesn't have to look like this. It can be longer and thinner and more compact. Your valves can be rectangular as opposed to circular. You don't have to have one big valve, you can have lots of little valves. You don't have to have one entry point, because we're doing a single thing where we take one bellows and we put it to one valve chest. If we want more bellows, there's nothing stopping us having more bellows. We can have more bellows run from the same drive unit. Now I've put these connections here because I'm going to connect those two like that. But you could equally put a manifold in there where you have 4 of them, either straightforward in a line, or 4 stacked on top of each other, or 2 in a line, and 2 by 2 grid. Doesn't matter. You would then create your manifold to connect these to a single box which would connect to your valve chest. So we'd put a manifold in there to create more of these. Of course, you could just make bigger ones of these and still have one entry port to your valve chest. It really depends on the design decisions you make. So I'm sure, as you can see, just from these 2 components, there are lots of decisions you have to make. Now we know that this component here will shift 1.2 litres of air every revolution, and there are 25 revolutions. So we know the volume of air that this thing will actually shift. If you want a greater volume of air moved, build more bellows or build your bellows bigger. It will mean you'll have to work out what volume of air you want moved per hour. But that's not challenging, just measure your room and work out the volume and use that. So you'll have a certain volume of air you want to move, and clearly you should match your bellows to your requirements and the volume that you want. Now this is a really nice little unit, and you could make a multiple of these units, but like I say, you could make one big unit where you have a big bellows but it's quite thin. Then your whole device will be much more compact. Again, you're choosing places where to drive it. You can drive it from here, or you can drive it from here. Now I've chosen this drive unit because it's something I had. It's extremely low power. So this is a 12-volt motor, meaning you can run this off a car battery if you wanted to. And I like that idea. AC is really power hungry, and it's one of those things that's difficult to convert when you're actually doing off-grid. You need something else. Normally you have an inverter. Here we could run it directly from the 12-volt supply, and that's important to me, because if you can run it without inversion, then you're not going to get energy losses from your battery bank through your inverter to your AC motors. So here we're using a 12-volt DC motor. It's a window winder motor, and it runs at 25 RPM, which might be a bit slow for you, but you can get these quite easily up to 100 RPM, in which case you'll get 4 times the volume of air shifted for this size by upgrading your motor. Of course it'll use a little bit more energy, but you can still do that. So the choices you're making are going to be factored into what it is that you want to achieve. Now, if you don't want to do any of this, buy yourself an AC unit, why not? If you want to do some kind of saving, then being able to run it from a 12 volt is actually brilliant. As I say, with this logical block, it's all about moving the air. any way you find to move the air. I like Bellows. I like Bellows because they're efficient and cheap to run. This logical block is all about air direction, and it allows us to use energy that is otherwise being unused and would escape. So those things together, the lack of the use of the inverter, the recapturing of what would be lost energy, they're going to increase the efficiency of this overall system just because of those reasons, and that is awesome. But you could incorporate those into a standard AC as well. So a standard AC, if you start tapping into that energy source, then you're going to make a saving because you're not reheating something twice or recooling something twice. Room ACs actually are perhaps amongst the worst for energy efficiency. If you think about it, you've got the one side hot, the other side cold. The cold side's blowing the air out to you, but the hot side's still in the same room, and it's still heating up that room air. So you're having to cool down the air twice because you're heating it up again. I mean, what they tried to do is put one of these vents out through the window and blow the hot air out through the window. But the motor, the compressor, it's still sitting in the room. It's still generating heat and it's still warming your room, even if you have that vent dangling out the window. So those things are recooling air that they are on themselves heating, which means they're just terrible in their efficiency. And that's no real surprise. It's why AC units, incidentally, are split systems. In a standard AC unit, the compressor side very often sits outside. That's just so you're not recooling the air that the compressor unit is reheating for you. It makes them really, really more efficient. So split systems are always more efficient than a combined system sitting in one room just because of the heating aspect of it. So this logical block we're talking about, we've got those two blocks that we need, and we've got to think about them in terms of the volume of air we want to shift and the efficiency and the reuse of energy that would otherwise be lost. The next thing we do when we're moving that air as efficiently as possible, of course, is blow it over something like this, a radiator. It's just something to cool the air down. I mean, it's quite common to cool them and dehumidify them at the same time. That really depends on your situation. I mean, if you're in Florida, which is just pardon me for people who live in Florida, but in summer, the humidity in Florida, it's awful. And I don't think anybody would disagree with that. So you probably want to dehumidify the air as well as cool the air. And that's just an aspect of what you want to do at this stage. Now, I live in England, and it's not that troublesome. Actually, we don't have that much AC, so me having a bit of humid air doesn't really bother me. I just want it cool. So my need is to cool the air, so I put a straightforward radiator in there. I might want to dehumidify it, in which case I'd put something in there to suck the water out. Calcium chloride will do that just as well. So if this went through a tub of calcium chloride, it would absorb the water and we'd get dry air out the other side. But here all I'm going to do is this. Now it's only this size and only laid out in a line to demonstrate what the logical blocks are. There's nothing to stop me using a bigger radiator. So I got this, of course, from my car. Now clearly there's a mismatch. This is massive, this is tiny. What do I do about that? Well, as I said before, I could either make one big square bellows that fits this whole thing and blows in and out through that whole thing, which would be really super cool. Or I can make lots of these little ones, a manifold, and then put the manifold on there so that we have one entry point spreading out in a cone. There's a huge amount of things I could actually do with that, but the logical block doesn't change. It's just the implementation of what you want to do. Okay, this is something I picked up from the roadside. It's a wine cooler. So if I really wanted to do it that way, of course this contains a radiator, a compressor and a plug to plug it in the mains. I could just rip that whole thing out and use that whole thing from the wine cooler to make my air conditioning, and it would go here where the cooling system is. Okay, So I wanted to show all of those things before I basically seal up the valve chest and connect it to this, and talk about those design considerations. A lot of design considerations are going to be up to you, but the logic of what it is that you're going to do, the blocks that you require, are always going to be the same. Okay, so to illustrate those ideas, I've swapped this smaller bellows out to this absolutely massive bellows. This one is made out of this stuff. It's cloth tape. So you just put the stiffeners down and cover it with cloth tape, and if you want to know how to make it, then just follow the How to Make a Bellows video. But this will clear 18 litres every stroke, which is really a huge amount of air. It does obviously take a little more power to move it, but it clears an awful lot of air. And it's attached to the valve chest. I quite like it actually because it sounds like breathing, but have a listen. That's awesome. Let me give you a close-up of the valve actually working. So there's the valve there, it's kind of loose, and if I press the bellows in, you see the valve pop out and all the air rushes out. When I pull the bellows out, you can see the valve pulls shut, and it's quite shut, and then open again, closed. It's giving out quite a blast of air, that actually. So like so many other things, the reason this isn't just a whole load of instructions, cut this, cut that, cut this, is because every situation, what you want to do is going to change. And that's why I think it's important to look at the different varieties, size of bellows, type of chest, organisation. I mean, we've got this way. We could put it up and down if we wanted to. It really just depends what you want to do. What you have to remember are the key logical components contained in air conditioning, and replicate those in a way that you like. Now, I like this design. I'm a very steampunk kind of guy. I love steampunk, and at the end of the day, this will probably end up looking extremely steampunk, which is why I quite like this black leatherette bellow. But we'll continue with this, and I hope you're finding the video series interesting, and thank you very much for watching.